Hello again. Thanks for joining us on Space Nuts. This is a Q&A edition. My name is Andrew Dunkley. What's a Q&A edition? It's an edition where we get Qs and give you As because you're so clever. Something like that. Anyway, we're going to answer audience questions. That's what I'm getting at. We've got questions about Redshift. We've got questions about dark photons. What? We've got questions about deep space astronomy and another one about the expansion of the universe. I think we talked about that last episode. Anyway, we'll see if we can solve all of that on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And with us again to kind of try to maybe answer some of that is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Kind of is probably the best description, really, isn't it?
Possibly so. So. But, it's good to get questions. We've got a whole new batch, so let's get stuck straight into it. Now, first question comes from, I love the way he always ends his questions. I'm not going to reveal anything, but let's hear from Roger.
Hey there, Space Nuts. This is Roger, the truck driver. Tonight I'm in Rutland, Vermont. I got a question about the redshift of galaxies. If the light that we're seeing from a far off galaxy is shifted to the red and it started out at a higher frequency, doesn't that mean energy's lost somewhere between here and there? And is that energy just transferred into space? And if it is, does that contribute to the expansion of space? And I'm not saying it's dark energy, but does it contribute to it? Or does that energy get dissipated in another way? All right, always digging the show. You guys keep on trucking.
I love that. We've got train drivers that do that. Unfortunately, they do it at 3 o'clock in the morning. Although today he did it at 10 to 7, I was pretty annoyed.
This is the one going past your place.
Yeah, behind our place there's a rail line. It doesn't get used a heck of a lot, but when it does, yes, the glasses rattle. The ones on my face, I mean. Thanks, Roger. Great question. The change in frequency with the energy loss, where does the energy go and does it contribute to the expansion of the universe? And could it possibly be maybe not dark matter or dark energy or something?
Yeah.
There's a lot. He packed a lot into that question.
He did. And it's a great question too. It's Roger's absolutely right. The conservation of energy, energy can't be created or destroyed. That's the fundamental rule. Energy is always conserved. But the universe doesn't play by the ordinary rules. It's an interesting answer here. And I have to say, it's changed my view of what what the answer to this problem was.
Okay.
Because when we've been asked this before, we haven't been asked it for a long time, I just assumed that the energy basically was absorbed by the universe, by space-time, and maybe contributed to the expansion, although you can't have it both ways because it's the expansion that's causing the photon's energy to be lost. And just stepping back, exactly as Roger said, you've got light going through the universe. Its wavelength is being stretched by the expansion of the universe. Therefore, the light is losing energy because the energy of a beam of light is all about the frequency of the light, in other words, or the wavelength, putting it another way. So if you increase the wavelength, you lose energy. And that's a given already. So what I used to say was, yes, it kind of goes into the universe, but I've done a bit more reading on this, and I was wrong.
Ooh.
Because when you apply general relativity to the universe as a whole, and that's the as we've talked about, and we talked about it at length in the last episode, it's the kind of fundamental rule that governs everything that we understand in the universe. When you apply general relativity, that conservation of energy that we expect to happen in the everyday world, it doesn't hold good. So energy is not conserved in an expanding universe.
Oh.
And so basically the energy simply disappears. It's just not there anymore because of the expansion of the universe. It's not causing the expansion of the universe. It's not contributing to dark energy or dark matter, the energy loss. It just vanishes.
Wow.
So work that one out.
I can't.
No, I can't either. I kind of really need to look at the equations on this.
You don't show them to me. I mean,
I'm not that keen on looking at them myself either. I've got too much else to do. But that is the thinking on this. And I think the conservation rule does not work when it comes to the universe on a whole.
Yeah. Wow. Gee, that's quite a revelation. Who figured that out?
It's on a number of different physics related websites.
So there's the reason no one knows about it, because it's physics, and who reads that stuff?
Yeah, I think the relativistic bit of it comes from the fact that the energy of a particle, which is what we're talking about, it's an observer-dependent quantity. And so that's why relativity plays a part in this, because you're the observer and you're talking about something that's relative to another observer, i.e. the photon.
Yeah.
And that's why you've got a relativistic access to it.
Wow. Okay. Great question, Roger. I'm not sure you were expecting that answer, but there it is. The energy just gone, goes, vanishes, ceases to exist. It's a dead poly. So anyway, no one got that joke. I was doing a Monty Python skit for some reason.
Yeah, you were. That's right.
Yeah.
I'm pursuing this in a little bit more detail and just trying to, see whether we've got alternative
Theories.
views of this.
Well, generally speaking, you do get alternative views when it comes to this kind of thing.
Right. So that's right. I think the standard explanation today is that energy is not conserved.
Okay. We'll leave it at that until somebody throws another spanner into the...
Yeah, we might be giving a different answer next week.
Could be. Thanks, Roger. Great to hear from you. Toot, toot. We'll catch you next time. Our next question comes from Peter. He's from San Diego, California. While listening to another astrophysics podcast, I heard the term dark photon for the first time. Apparently, this is a particle astrophysicists are seeking in order to explain dark matter and or dark energy. Could you please elaborate on what a dark photon could be? Dad joke for Andrew, a photon travels at the speed of light. Does that mean a dark photon travels at the speed of dark? I like that. That's good.
Yeah.
That's really good. Keep up the great work, he says. Thank you, Peter. Hope all is well in San Diego, California. Have you ever heard of a dark photon, Fred?
Yes, I've probably got a few in this box here. The speed of dark, just going back to that quip, there was a story I read probably a fortnight ago about exactly this, in that darkness can move faster than the speed of light.
No.
It's an illusory darkness. It's when you've got light beams interfering with one another so that you've that and interference light beams can cancel out. So if you've got two light waves and you add them up out of phase, they can cancel out and you get darkness.
Okay.
That's a well-known principle of interferometry.
Yeah.
I used to play with that when I was a student a lot. But there are certain circumstances that those patterns of darkness can actually exceed the speed of light because they're not actually real. They're not real entities. They're not a thing that's carrying any sort of information or energy. They're just patterns in an interference pattern. They're just dark patches in it. And I think under certain circumstances, they could go faster than the speed of light. So darkness might be not quite as, as twee as you thought it was.
I guess not.
Anyway, that's not the question, because dark photons are definitely something different. And they're basically hypothetical. They've been hypothesized by physicists and cosmologists as being a force carrier, similar to the ordinary photon, but related to dark matter. In other words, you might have... Sorry, somebody's trying to phone me. I'm just going to kill that call.
Yeah. That was me. That was me. Well, no, it wasn't.
They're part of there may be, when we discover finally what dark matter is, there may be a suite of dark particles, which could include dark photons. That's the bottom line.
Right.
And so, we mentioned last week, in the last episode, the Large Hadron Collider being upgraded to be the High Luminosity Large Hadron Collider. That's one of the things they'd be looking for will be dark photons.
Okay. I tried to do an AI search for an explanation on it, and it sort of gave me all this gobbledygook. But what would a photon do? It says it would carry a force within the dark sector. We call that the government. It might allow dark matter particles to interact with each other, and it could very weakly mix with normal photons, giving us a way to detect it. And the reason they reckon that scientists care about this is, as you said, could explain what dark matter is made of.
Yep.
So therefore solving some of those gaps in our current physics theories. So that's why people are interested in this, and that's why they're upgrading the Large Hadron Collider, and hopefully we will learn more in years to come. That's the hope.
That's the hope, yeah. So we might, we might be talking one day about dark photons having been detected, which would be a coup for space newts.
Yes, it will. But at this stage, they are not proven. It's just a theory. So that's about as much as we know at this point in time. But very good question. And thank you, Peter, for sending it in. This is Space Nuts with Andrew Dunkley and Professor Fred Watson. Let's take a short break from the show to tell you about our sponsor, NordVPN, and to discuss your online privacy. Because let's face it, these days, whether you're browsing at home or jumping onto public Wi-Fi at a cafe or an airport or wherever, your data is constantly at risk. Hackers, trackers, even companies you've never heard of, they're all trying to get a piece of your digital life. And that's where NordVPN comes in. Our sponsor is fantastic. It's one I've been using for many years now myself, and I have absolute faith in their product. NordVPN encrypts your internet connection, hides your IP address, and keeps your personal information safe from prying eyes. It's like putting an entire online world inside a secure tunnel. They've got over 7,700 servers worldwide. You can browse fast, safely, and without restrictions. Plus, features like threat protection and ultra-fast speeds with Nord links mean you're not sacrificing performance for security. You get both. Right now, you can grab our special Space Nuts deal and get 4 months extra for free. Plus, there's a 30-day money-back guarantee, so it's completely risk-free to try. Just head along to our special URL, nordvpn.com/spacenuts. That's nordvpn.com/spacenuts, and don't forget to use the code SpaceNuts. That's nordvpn.com/spacenuts. Stay safe, stay private with NordVPN, our sponsor.
0G, and I feel fine.
Space Nuts.
Okay, Fred, we'll move straight on to our next question, which is another audio question from Eli.
Hello, this is Eli from sunny Coachella Valley in California. I'm embarrassed to admit it, but I still can't get my head around deep space astronomy. I get that the light from, say, a distant galaxy is 1 billion years old, but why that particular point in its time? Is it just a matter of whatever light is hitting us is the time we get to see? But for really early light, the JWST early universe stuff that's been traveling for 13 billion years and just hitting us now, are we looking for the light that hasn't passed us by or hasn't made it here yet, but is from that one precise location long ago? This stuff is so difficult to get my head around. Love the show and hope you guys can clear this up for me.
No, we can't.
you.
We just thought we'd put the question in there. Thanks, Eli. This is a deep. I'm not only in deep space astronomy terms, but it is a deep, deep topic. I mean, when we look up into the sky at night and we see all those beautiful coloured dots, we are looking at history. And it's variable history because some of it's 4.41 light years away and some of it's 400,000 light years away. Some of it's further than that. It's But then you've got the cosmic microwave background radiation, which is kind of a leftover of what happened after the Big Bang, and that's a different kettle of fish. And I can understand why you got a headache, Eli. Over to you, Fred.
Thanks. So I guess that I understand Eli's issue as well. So you've got to be in the right place at the right time to see a photon from a distant galaxy. But I guess the way to envisage this is if you think of the universe, and you've got to perhaps think of it as if you were looking at it from the outside, which we never can. But if you can think of it that way, then it's full of objects which are radiating light. Even in its infancy, when the universe was very young, the stuff in it was basically shining. Once we got past the dark ages where no stars were shining, and those are the galaxies that we now see. So they're constantly radiating light, and that's just like a river of light that's flowing down time, if I can put it that way. And a long time in the future, it reaches us. But it's not just, an individual photon or something that's reaching us. It's this stream of stuff that is being radiated throughout the universe by these galaxies. So we pick it up. We pick it up sometimes, exactly as you've said, well up to 10 billion years after it's been radiated. I think 12 billion years are the oldest or the earliest galaxies that we now see. We're looking back in time 12 billion years and seeing them as they were perhaps 1.5 billion years after the Big Bang. And they're shining, they're radiating light in the early universe, and down the track that reaches us, because that light's going in all directions. So it wouldn't matter where in the universe we were, we would still see them. We'd just see them in a different position in the sky if we were a long way from where we are now.
Yeah.
So I guess it's, in a way, one way of thinking about this is if you imagine us on planet Earth here, and imagine us being surrounded by a whole series of shells which we're at the center of. And this is a bit like the crystalline spheres that people used to think the universe was made of. But these shells, spherical shells, all centered on the Earth, but each one clicks over to a time further in the past. Because the light's coming to us from the whole cosmos, which is full of stuff, and that's why we can see these shells sort of being illuminated in a way by the objects that radiated them at that time. That we see them because of the distance that they are away from us means that the light has taken that long to get to us. I don't know whether that helps or not. In fact, I think I've just confused it completely, but.
I'm just doing a little experimental search here for a sec. What I agree with in terms of Eli's question and getting your head around it is if Betelgeuse, or however you want to pronounce it, went supernova right now as we were speaking, we wouldn't see it for 640 years.
Yep.
So for it to have gone supernova in the past and us to witness it, it has to have happened pretty close to 640 years ago. Does that make sense?
Yes. So you could think of that in another way. Anywhere between us and 640 light years away, there could be this pulse of light that's on its way to us from Betelgeuse. It would spread out in a sphere, and as that sphere expanded, eventually it would wash over the Earth and we'd see it. And perhaps see it during the day as well, because it might get bright enough to do that. And I think that's a really good way of putting it, Andrew, because thinking about the galaxies, they're just streaming light out all the time. But something like a supernova explosion, which gives a big pulse of light, that's perhaps easier to get your head around, because that's just got to it'll take whatever time is represented by the distance away. So 640 light years away, it'll take 640 years to get here, for that pulse to get here. But then it will sweep over us, and we'll see the light fading away.
Yeah, and the reason I chose that target is because there's a lot of conjecture about its future and the possibility that it's reaching that critical mass point.
Yes.
But it could have already happened. That's the other thing.
Yeah. But that's something we can have no knowledge of. That's the key thing, because we are limited by the speed of light. That's the thing that always limits our view of the universe.
And just to confuse Eli a little bit more, there are probably things in the universe we will never witness because the light is just too far away to reach us in any reasonable amount of time, even beyond the life of the Earth itself or our sun. There are things we will never ever know about.
Correct.
It's and that's where it just gives you one of those headaches that requires you to take paracetamol and ibuprofen at the same time. Deep headaches. But Eli, great question. I'm not sure we solved your problem, but anyway, I try to explain this sort of stuff to my grandson and my granddaughters, and how do you explain time and distance to a young child, and when you're trying to get through traffic, it's
that might not be the best time to do it.
Probably
really.
not, but they're very interested.
Yeah,
very interested. Good. Thanks, Eli. Great question.
The crew of Artemis II now bound for the moon. Humanity's next great voyage begins.
Space nuts.
Our final question comes from Nova Scotia. It's from Ken. Look, this is an old chestnut. We've probably spoken about this many times, but it's always good to revisit. If the universe is expanding, what is it expanding into? And also, is the universe spherical?
So, yes, what's it expanding into? Well,
we don't know, and yes.
Yes, it's actually we don't know, and maybe.
And maybe. Yeah. Okay.
So the universe is everything that we can detect. That's the definition of the universe, everything we can measure or detect. And that means, and we observe the expansion, but we don't know whether there's an edge to the universe. We don't know whether it's infinite. We don't know anything beyond the horizons that we see. And the most obvious one is the cosmic microwave background radiation, beyond which we can't see. But the universe almost certainly goes on beyond that, probably for a very long way, maybe very big. But we've got no knowledge of a boundary or any other medium that it might be expanding into. So one possibility is the idea of multiple universes, and they might exist maybe in a higher dimensional arena, if I can put it that way. You know, if you can find that there are extra dimensions, we know the 3 dimensions of space and 1 of time. That's what we've got now. But if there are hidden extra dimensions, maybe they provide a venue for the universe to expand into. And there are various theories that accept that. M theory is one of them, where M is probably an abbreviation for membrane. The idea is that the universe can be collapsed onto a 2-dimensional membrane, and there are lots of these membranes in the universe, in the kind of higher dimensional universe. But that's just conjecture, and we've got no mechanism for proving that. At the moment, the only thing we know with certainty, with absolute certainty, is that the universe is expanding.
Yes, at an accelerating rate, although the accelerating rate's not as accelerating as it once was, possibly. Yeah, there's 3 possible shapes of the universe. He asks if it's a sphere. There's the flat universe theory. Oh, do we have to go there? There's the closed universe theory, which is the positive curvature, so a sphere. Or the open universe theory, which is negative curvature, so it's more like the shape of a saddle. From what I'm reading, the most popular likelihood is the flat universe theory.
Yeah. But it's only flat in a Euclidean sense. It doesn't mean it's shaped like a tabletop. It means that parallel lines never meet, basically.
Yeah.
That's what we mean by flat. It's the shape of the geometry.
And the other thing that they suggest is that, it can be flat and still expanding, as you said. It might be infinite. We've talked about that before. And there is likely no center and no edge.
Correct. That's what we believe.
Yeah.
Now, as to its shape, so basically, I think Ken's question is it spherical? And we don't know the answer to that. We know that the volume within which we can detect is spherical because the cosmic microwave background radiation forms an imaginary shell all around our galaxy, and it's the same distance in every direction. So in that regard, it's what we call isotropic, the same in all directions. And that's really the only thing we can lay it down to. But there are ideas that if you looked at the universe on a bigger scale than we could see, it wouldn't be, that it might be different in different directions. And that, in fact, has been hypothesized as one of the sources of dark energy, that when we're just seeing a local bit of the universe that's expanding, whose expansion is increasing, whereas somewhere else it might be slowing down the expansion of the universe.
Sorry, go on.
No, that would be a universe that's not isotropic. It's not the same in all directions. But we assume it's isotropic, so that's all we can do in our assumptions in cosmology. We
just can't see beyond what we can see, which sounds stupid, but that's the way the universe is.
Yeah.
We've got the known universe and then the rest.
That's right.
Basically.
And the rest might be a lot bigger than the known universe.
But we just don't know. The only thing I thought of is like you look at Earth's atmosphere, and as you go out, it thins, and so there's no defined line between space and the Earth proper. Could the universe be of the same ilk?
Yes, but that would imply that space-time just sort of keeps on going. It just might be empty. Yeah,
I don't know.
Don't know, man. We don't know.
We don't know.
Why are you asking us? We don't know.
Oh, dear. Thank you, Ken. Very thought-provoking question, and thanks for sending it in. If you have questions for us, please send them to us via our website, spacenutspodcast.com, spacenuts.io. There's a little button at the top called AMA, and that's what you click on to send us text and audio questions. If you've got a device with a microphone, you're all set. Most smartphones and smart devices have that, and you can send it to us in audio form. Don't forget to tell us who you are and where you're from, or you can send us a text question, just fill in the blanks. And while you're there, have a look around, visit the shop, get something from yourself, whatever you like. And we're done. Fred, thank you so much. That was a tough one.
Yeah. Well, Space Nuts always probes the limits of knowledge.
It does.
That's what we do.
Unfortunately, I have such limited knowledge. I'm not very helpful, but glad you're here.
No, you are very helpful. And so are our listeners, because they keep on probing, which is great.
They do indeed. All right, Fred, thanks very much. We'll catch you on the next episode.
Sounds great. Thanks, Andrew. Professor
Fred Watson, astronomer at large. And thanks to Hugh in the studio, who couldn't be with us today because he's been expanding at an accelerating rate, so he went to the gym. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.